Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC709. Topic light emitting diode. Let us discuss some basics of semiconductors. Doping means adding impurity to the pure semiconductors. The pure semiconductors are germanium and silicon. These are examples of pure semiconductors. And impurities are trivalent and pentavalent. By adding trivalent impurity to the pure semiconductors, p-type material are formed, and by adding pentavalent impurity to the pure semiconductor materials, n-type materials are formed. Here you can observe the formation of n-type material and p-type material. In n-type material, free electrons are created in conduction band, and in p-type material, free holes are created in valency band. N-type material, majority charge carriers are electrons, minority charge carriers are holes. By donating free electrons to the conduction band, uh, the atoms become positively charged immobile ions. Majority charge carrier concentration depends on number of donor atoms, and minority charge carrier concentration depends on temperature. By adding majority charge carriers, donor atoms become positively charged immobile ions. Here you can observe the positively charged immobile ions in n-type material. Next, p-type material. In p-type material, the majority charge carriers are holes and minority charge carriers are electrons. Majority charge carrier concentration depends on acceptor concentration, and by creating hole, the atoms become negatively charged immobile ions. Once again, I will repeat. Majority charge carrier concentration depends on acceptor atoms, and minority charge carrier concentration depends on temperature. Either it is p-type material or n-type material, the minority concentration always depends on temperature. By generating majority charge carriers, acceptor atoms become negatively charged immobile ions. You can observe the negatively charged immobile ions in p-type material. The next concept is recombination. It is a process of conduction electrons filling holes in the valency band, thus eliminating electron hole pair. Means here uh, it is valency band, it is conduction band. When electrons fall from conduction band to valency band, some amount of energy, that is called photon energy, represented by HMO, will be released. This photon energy is equal to the energy gap. It is the energy gap between the valency band and conduction band of the given material. When electron falls from conduction band to valency band, uh, it recombines with hole. After recombination, electron hole pair will disappear. This concept is used in the principle of light emitting diode. Direct band gap semiconductors. In direct band gap semiconductors, the peak energy level of valency band and the valley energy level of conduction band, they are at the same momentum, at same k value. Uh, the direct band gap semiconductors are gallium arsenide, gallium phosphide, gallium arsenic phosphide, etc. These materials are used as base semiconductor materials in light emitting diode. Indirect band gap semiconductors. In indirect band gap semiconductors, the upper energy level of valency band and the lower energy level of the conduction band, they are at different momentum, they are at different k value. It is at, let us say it is at k2, it is at k1. Here k1 is not equal to k2 in indirect band gap semiconductors. The example of indirect band gap semiconductors are silicon and germanium. Refer to the semiconductor material and their band gap energy. Light emitting diode. Light emitting diode is a diode which emits visible light when it is forward biased. It works on the basic principle called recombination. It is the symbol of light emitting diode. Normal PN diode with arrows. Uh, it is the symbol for light emitting diode. Now here once again I repeat, when electron fall from conduction band to the valency band, it recombine with hole. After recombination, electron hole pair will disappear. During the recombination process, some amount of energy will be released, and the released energy EZ is equal to H C by lambda. Here, the energy is associated with the wavelength. Uh, if the released energy photon wavelength is in the range of optical signal, then the emitted light can be visible to our eyes. Light emitting diode. Why silicon and germanium diodes cannot be used as LED? Here, silicon and germanium are indirect band gap semiconductors. For silicon, the energy gap is band gap energy between the valency band and conduction band is 1.1 electron volt, and for germanium it is 0.7. Here, the energy gap is associated with the wavelength of the optical signal. So the corresponding value of wavelength do not fall in visible region when the type of semiconductors are indirect band gap semiconductors. Germanium and silicon will not contribute to generate optical signal. Here, the semiconductor materials like gallium arsenide, gallium arsenic phosphide, gallium phosphide, which are obtained by mixing group 3 elements with group 5 elements. They are indirect band gap semiconductors, and their energy gap is in such a way that here Ez is equal to Hc by lambda. The wavelength of the signal generated is associated with the optical energy which falls in visible region. For that reason, direct band gap semiconductors are used as base materials in manufacturing light emitting diodes. Once referred to the base semiconductor materials used for the manufacturing of light emitting diode. Double heterojunction structure of LED. In figure 1, you can observe the double heterojunction structure of LED. The structure consists of gallium arsenide, aluminum gallium arsenide, double based heterojunction structure. Here, uh, if you observe, the gallium arsenide material is sandwiched between aluminum gallium arsenide and uh, two aluminum gallium arsenide materials. Here it is aluminum gallium arsenide, it is gallium arsenide, it is once again aluminum gallium arsenide. Now, uh, the energy gap, band gap energy for uh, the p-type material, it is gallium arsenide. Its energy gap is around 1.43 electron volts, and for aluminum gallium arsenide the energy gap is 2.1 electron volts. The structure of energy band diagram is very important to describe the phenomenon of light emitting diode based on the principle of recombination. Double heterojunction structure. When forward bias is applied to the double heterojunction LED, electrons are injected from highly doped uh, aluminum gallium arsenide layer to the central P minus, that is middle layer or active layer. The injected electrons are trapped in the middle layer. The middle layer is called active layer. Here, due to double heterojunction structure, the potential barrier is EZ2. It is EZ2. Energy gap for aluminum gallium arsenide, and it is EZ1. Energy gap for gallium arsenide. EZ2 is greater than EZ1, existing on both sides of the middle layer. This layer is called active layer, where the recombination takes place. Now here the electrons are forced to recombining radiatively with the energy equal to the energy band gap of gallium arsenide. Means here if we apply some, it is P when it is forward bias. Uh, when it is forward bias, what will happen? Some electrons will enter from the n-type material to the active region. Here the middle layer is p-type material, so the electrons which enter from n-type material to the p-type material, they recombine here in active layer. After recombination, electron hole pair disappear and some uh, amount of photon energy will be released. If the released energy falls in the wavelength of optical light, then we can call it as the formed diode is light emitting diode. As a recombination between the electrons and holes is limited to narrow central pot, the internal quantum efficiency of such LED is higher when compared to single junction LED. Here, in the structure of LED, mostly double heterojunction structure is preferred when compared to conventional normal p-n diode structure. The reason is the internal quantum efficiency is more for double heterojunction structure. The LED configuration being used in photonic communications are surface emitters and edge emitters. In most of the cases, edge emitters are preferred over surface emitters. The surface emitter, once referred to the schematic diagram of surface emitter, it is the structure of double heterojunction, and where this is the position of active layer from which the light will be emitted. The circular active layer is in practical surface emitters is normally around 50 micrometer in diameter and up to 2.5 micrometer thick. Once refer to the schematic diagram of surface emitter. In surface emitter, the plane of active light emitting region is oriented perpendicular to the axis of the fiber. That is here, if it is surface emitter, now this is a position of light emitting diode. It is the position of core area. The orientation of emitting region is perpendicular to the axis of the fiber. If we construct the structure like this, then the emitting region and core position are perpendicular to each other. The emission pattern is essentially isotropic with 120 degrees half power beam width. The isotropic pattern from a surface emitter is Lambertian pattern, means it is equally bright when viewed from any direction. Edge emitting LED refer to the structure of edge emitting LED. Here it is the position of double heterojunction structure, and it is the active layer where the light will be emitted from. The length of the active region is ranging from 100 to 150 micrometer. The edge emitter consists of active junction region and two guiding region. You can observe the light guiding regions in surface emitting LED structure. The guiding layers both have a refractive index which is lower than that of active region but higher than the refractive index of surrounding material. The emission pattern of edge emitter is more directional than that of surface emitter. So in most of the applications where LED is used, in that edge emitters are preferred. Internal quantum efficiency. The internal quantum efficiency of light emitting diode is defined as the ratio of RR, it is eta int is equal to RR by RR plus RNR, where RR is the radiative recombination rate and RNR is non-radiative recombination rate. And in terms of lifetime, the radiative lifetime is represented by tau R. Non-radiative recombination time is represented by tau NR, where N is the excess carriers or carrier concentration. Electron carrier concentration. Now, the internal quantum efficiency in terms of tau r and tau nr. The bulk recombination time, it is represented by tau. The relation between bulk recombination time, radiative recombination time, and non-radiative recombination time is given as 1 by tau is equal to 1 by tau r plus 1 by tau nr. And the theoretical quantum efficiency, internal quantum efficiency in terms of bulk recombination time and radiative recombination lifetime. The next is optical power generated internally. Here, once again refer to the formula of internal quantum efficiency of LED. Now here, eta int is the internal quantum efficiency in the active region. The optical power generated internally in the active region of LED is given by P int is equal to internal quantum efficiency I by Q, current injected divided by electron charge. H mu is the photon energy. Here mu can be replaced by C by lambda. Now the formula becomes the internal power generated P int is equal to eta int internal quantum efficiency Hc I by lambda. Hc by lambda is associated with photon energy. Now here P int is the internal optical power, I is the injected current to the active region when the light emitting diode is forward biased. Once again refer to some simplifications. If required, you just go through the PPT. The next is external quantum efficiency and external power emitted from the LED. The external quantum efficiency of a light emitting diode is the number of photons emitted from the LED to the number of photons internally generated due to the recombination process. Now here external quantum efficiency formula can be written as eta external is equal to 1 by n1 plus 1 square. Here n1 is the refractive index of semiconductor material active region. It is the refractive index of active region, and n2 is the refractive index of the outside material. In general, the outside material refractive index is 1. Now here the optical power output emitted from LED is given by P out is equal to external quantum efficiency multiplied by Pi. Some simplifications to determine internal quantum efficiency and net power are radiated out of a light emitting diode. Refer to the formulas. Sample problem on light emitting diode. Refer to the solution. Based on the standard formulas available, you can solve the problem. One more sample problem. Refer to the solution. By simple substitutions, you will get the answers. Thank you. We will meet with the next lecture.